Hey everybody, this is 7D, forces versus torques. That's hard to say, forces versus torques. Forces versus torques. Scenario is a box of mass M is tied to a rope that is wrapped around a pulley. The pulley is initially rotating counterclockwise, like indicated here, and is pulling the box up. The box slows down, that is going to be important, and stops instantaneously and then moves back downward. So we came in and see me turned the corner and walked into the room, and this box was getting wrapped up around the pulley, but it was slowing down, and then it's gonna stop and come back here. All right, so first thing is they're gonna have us think, they're gonna make why it's called forces versus torques, is they're gonna have us think about some of the ways in which forces are similar to torques and then some key differences. So it says the dot below represents the box. Draw a free body diagram showing and labeling forces, not components, exerted on the box initially. Draw the relative lengths of all vectors to reflect the relative magnitudes of forces. Each force must be represented by a distinct arrow starting on and pointing away from the dot. So here's the box. What are the forces on it? Well, it's here on Earth, so 1, 2, 3, 4, 5, I'll just say, no reason, just so I got that in my head how long that is. There's a force of gravity on that box. And if we look at the picture here, what else is acting on it? A tension. So the box has a rope on it, and so there is a tension. 1, 2, 3. Now, how did I know? I drew my force of gravity bigger than my tension. How did I know to do that? Because it says the box is slowing down. So gravity is winning the fight. It is accelerating that direction there. So those are the two forces and the only forces on the box. Let's now switch to the pulley. It says on the diagram at right, draw and label forces, not components, that are exerted on the pulley as it initially rotates. Clearly indicate at which point on the wheel each force is exerted. This is different than a free body diagram, because when we do torques, we need to be concerned with where it is. On a free body diagram, we just imagine the whole object as a little dot. But when we think about things rotating, we need to know where the forces are acting. Draw each force as a distinct arrow starting on and pointing away from the point at which the force is exerted. So the pulley also has a force of gravity on it. I'll just draw that in there. They don't give me a box this time, so I can't really draw how long it is. If we look at this picture, there is tension. So that rope will be pulling down on the pulley as well. So the tension on the pulley acts down over on the side here. And then finally, we need one more force. I have two downward forces. What is it? Well, this pulley you can see is hanging from this little pin right here. So I'll call it the force of the pin. And how big does it have to be? Well, roughly as big as both of these together. I'll call that the force of the pin there. So the force of the pin up balances out the force of gravity down on the pulley and the tension down. This is why the pulley doesn't accelerate up or down. It has nothing to do with if it's rotating or not. That's this question. What force is responsible for the net torque, not force, on the pulley? And that is caused by the tension. Why is it only the tension? Well, the force of gravity and the force of the pin cannot cause a torque. Why not? Because torque is force times lever arm times the sine of the angle between those two. And neither of these things have a lever arm. They're acting on the point of rotation. They cannot torque it. That's why the pulley will never start rotating on its own unless there's something to create a torque acting on the sides of it there. All right, next one. These confuse a lot of people, but they're so easy actually if you just think of their linear analogies. Sketch a graph of the angular velocity as a function of time from the initial instant until the weight comes back down to the same height. Take counterclockwise as positive. Well, think about it like this. If I said, draw the velocity of this box as a function of time, call up positive, and think about it like that. Well, okay, because it was initially going a positive direction like this. It started going positive, but it was slowing down. So its velocity approached 0. And then it came back down into this direction here. So that is what the angular velocity of the pulley looks like. At first it was spinning in a positive direction, and then it slowed down its spinning until it wasn't spinning at all, and then it started spinning in the negative direction, which is clockwise. Notice if you'd called this velocity, that would look exactly the same for the box. So it confuses people with the spinning, but don't let it. It's the same stuff we've always been doing. So likewise, let's do a graph of the angular acceleration of the pulley. Think of it again as like the angular acceleration of the block. So what way is this thing being angularly accelerated? Well, the torque here on it is this way. It wants to torque it clockwise, which they call negative. A negative torque will cause a negative angular acceleration. And so you'll have a constant but negative angular acceleration. Again, if this was the block and we said not alpha for angular acceleration but just a for linear acceleration, what would be the acceleration of that block as a function of time? It would just be that, with a straight line down in the negative direction.